Thank you, and I would like to thank the organizers for putting together a great workshop and a conference. When I was growing up in Bangalore, this area was a favorite spot for picnic. And for picnics, there used to be a lake and we were always buzzed here annually. It was almost like an annual pilgrimage. So it's nice to make a mathematical picnic pilgrimage now as you grow older. So there have been some talks on Iwasawa theory already, but I'm going to do a quick recap for the benefit of some of the youngsters who are here. And I'm going to divide my talk into 3 parts. The first will be introduction, preliminaries. And second will be the players, where I'll introduce the objects that we are going to be studying. And then finally, I'll talk about the results. Okay, so notation. Oh, little below, okay. Where are the white chalks? And I'll keep some stuff here throughout because I'll be using things from there. So F will always be a number field. P will be an odd prime. And S is a finite set of primes of the number field that we are considering. And I'll always insist that S contains 2 classes of primes, which I'm going to denote by SP. These are the set of primes above P in F. And then I'll have an elliptic curve, which I'll introduce very quickly. And this will have to include the primes above the set of bad reduction primes for the elliptic curve. So E over F is going to be an elliptic curve. And then, of course, once you have fixed a prime, you are immediately interested in the behavior of the elliptic curve at the prime P. And there are 2 typical cases one considers, when it is ordinary and the other when it is supersingular. I'll say a bit about both, though the behavior is different. So here there are 2 cases, P ordinary, and the other is P supersingular. And by this, I mean the strong ordinary, by which I insist that all the primes lying above P, E is ordinary at all those primes, and similarly here, E is ordinary at all those primes above P here. And in this supersingular case, I'll mostly be restricting to F equals Q and AP equals 0. And this is sort of given to us. This restriction is forced upon us because I'm going to be talking about the signed Selmer groups, and these have been studied, defined only in these cases under this hypothesis. And to my, should say, shock and horror, when I tried to understand the behavior of elliptic curves at supersingular primes, I found that there are lots of these plus minus, sharp, flat, blah, 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 various things. And even the experts working in that area do not know how they are related, why they should be different, why can they not be defined for any other number field other than Q, and so on. So there's a lot of work to be done around this. And whatever I'm going to be talking about works in the broader context of ordinary Galois representations. For instance, representations coming from modular forms, which are ordinary at P, by which we mean that P does not divide the Fourier coefficient AP. But I'm not going to talk about those, just to keep the notation simpler and so on. But everything that I say, we have carried them over in this broader context, and people have generalized our work to Galois representations coming from Hilbert modular forms as well. Okay, so in this case, when you're studying this, of course, the holy grail in the arithmetic of elliptic curves is the Bird-Swinnerton and Dyer conjecture, and Iwasawa theory is one of the techniques that has proved somewhat successful in tackling that problem. And to do Iwasawa theory, it's counterintuitive. You are answering questions over the ground field, but in order to do that, you have to go to infinite extensions of F and then descend using the Galois action. So, and then of course, again in Iwasawa theory, there are these 3 themes 3 islands. So one is related to algebra, the other is analysis, and the other is arithmetic. And the intertwining subtext for all these 3 is the so-called main conjectures. And just to point out the depth of this interconnection, it's a big task to identify the right algebraic object that you're going to be studying. Here on the arithmetic side, it's usually the critical values of the L function, complex L function, or the complex L values. And here it's going to be the p-adic L function, which interpolates the complex L values. And all of these are deep projects on their own to understand the nature of this object as an algebraic object and to find the right p-adic L function and the exact interpolating formula for this. And analogous to the critical values or the values of the L function or the p-adic L function, what you have on the algebraic side are Euler characteristics of the Selmer group when they are defined. So we'll talk a little about these. So here's the situation. So I have Q, I have F, and then I have F cyclotomic. This is the ZP extension, cyclotomic ZP extension. Of F. This is the unique cyclotomic ZP extension, is the unique ZP extension contained inside the extension obtained by attaching all the p roots of unity. And so that's here. And by the way pairing, you know that all of this is a sub-extension of Fs, which is the maximal unramified outside S extension. And so here, again, because of the way pairing, there's another extension that we are going to be considering above F cyclotomic, but contained in Fs, and that's the one which trivializes the Galois representation associated to the elliptic curves. It's obtained by adjoining all the p power roots of p power torsion points of the elliptic curve. So f of e p infinity, or more generally what's called the false state extension, which is obtained by adjoining p roots of some integer m with some conditions. So this is like Kumar extension, infinite Kumar extension over the cyclotomic. So this Galois group is the simplest that you can consider after the cyclotomic one. It's non-commutative. It's a semi-direct product of ZP, 2 copies of ZP. And this extension, by Serre's theorem, we know that this is open inside GL2 ZP. So these two, this is as highly non-commutative as you can get. And classical Iwasawa theory studies objects over this or abelian extensions. I'm going to say a little about what we can do even in the non-commutative extensions. So the idea is simple. Once you define the objects, there's no reason to stop at a finite extension or at the cyclotomic extension or at an abelian extension, because the definitions carry over for any extension. But what you do with those definitions is the hard part. So we saw the definition of Selmer groups. So I'll always be dealing with, so let me first deal with the Selmer group. Yeah, and all these intermediary layers for any of these extensions, I will call them Fn. These are finite extensions embedded in these big extensions that I'm considering. So for any, so of course these are number fields again, and then you define the Selmer group, P infinity Selmer group. This is defined by the following exact sequence, which actually I would like to keep. Maybe I should remember not to erase it. So this is defined by Selmer, P infinity E over Fn goes to H1 Fs over Fn, EP infinity. And I'm not going to get into the detail of the local. I'll just denote them by JV EP infinity over Fn. These are the local H1s where the P comes out. It's H1 FNV E, the P primary torsion outside. Jacques, you have a question?
What is this extension?
That is this what's usually called the false state extension. So I take the cyclotomic extension and add p to the power nth roots of an integer m. It's like an infinite Kumar extension tower. There are some minimal conditions on m. For instance, there shouldn't be a power of p which is dividing m. Okay, I mean typically, okay, the way it arises in real life is if you take an elliptic curve having split multiplicative reduction. Sorry?
Global group?
Yes, it's a global. I'm taking the global Galois group. It has nothing to do with elliptic curves. I mean, like I said, it's the simplest non-commutative extension you can think of. Sorry? Exactly, analogous to what you get from trivializing the Tate curve at split multiplication. Exactly, it's a semi-direct product of two copies. Yes, it's a semi-direct product. So for instance, if you're working with a CM elliptic curve, then you can attach the P division points over f of EP, and there you would get ZP cross ZP. Okay, and so this is, I'm going to call this map lambda n, and the Selmer group is defined by the kernel of this map. And of course, once Fn is a Galois extension of F, this whole exact sequence, there's an action of the Galois group of Fn over F. So the Galois group of Fn over F, it comes equipped with a Galois action. So the Selmer group is really, you have to think of it as a module, as a ZP module with an action of this Galois group. But that doesn't help because these group rings are, you just have no way of understanding these group rings. And that's the reason you go to infinite or the group ring completions. And of course I can take inverse limit, and so that will give me over n, when I take the inverse limit, I get Selmer P infinity, P over F cyclotomic for instance, or later when I do it over the larger extensions, I'll put the corresponding larger extensions here, F infinity and so on. So respectively, F infinity goes to H1 over Fs over F cyclotomic, EP infinity, lambda cyclotomic, Venus JV of EP infinity over F cyclotomic. And of course, now this time it will have a Galois action of the whole gamma of the Galois group ZP. Okay, now this is an exact sequence. Let me call this star. So this is a sequence of discrete gamma modules. Sorry? It doesn't matter. For now, yes, but I can do this for any infinite extension. I'll take Fn's to be the finite layers. And I can take the inverse limit. Sorry, direct limit, sorry.
So
Yeah.
it's like one piece per layer or?
No, all of them, because once you choose all of them, that's when the Galois group acts on the places, right?
So that's why it's maybe one because of
It's not. Well, so that's why I said I'm not getting into the details of explaining the JVs. You have to take the direct limit carefully. Okay, so for instance, this is dealt with in detail in the book, my book, Galois cohomology of elliptic curves. Exactly. You know, but it's induced, from the decomposition group, it's the induced of all the places, right? Okay. So this, when I write JV in S, you should think of each JV as really being assembled from all the places that sit above V. It's not one place. And that's why I'm not explaining that in detail. All right, and now let's define the fine Selmer group. This is a Selmer group, fine Selmer group. Which I'm going to denote by R of EP infinity over, I'll do the same thing, Fn. This really is 0 R of EP infinity over Fn. It's like the local to global maps. H1 Fs over Fn, Ep infinity goes to direct some V in S, and I'll call it K1V of Ep infinity over Fn. So at the simplest level, for instance, when it is over the ground field, this is just going to be H1 Fnv Ep infinity. It's the real local to global principle that you have. It's the same H1. Whereas for the Selmer group, remember, when you take the H1, it is E and not Ep infinity, right? So that's the difference. Okay, so this is really like the SHA-1, if you like, what's usually called SHA-1 in the literature. Okay, so now again the same thing is true here. This is also, and then I take a direct limit, I can define it over the infinite extensions, Ep infinity over any infinite extension, F cyclotomic, F infinity, etc. Now this is again a sequence of discrete. And like I said, it doesn't, at the finite layers, you cannot study these as objects over the corresponding group rings. So you go to the group completion, and that leads me to introduce the Iwasawa algebras. So if G is any profinite group, and I take Gn, these are, so G, let me write G as the inverse limit of Gn's, okay, and the Iwasawa algebra, which I denote by lambda G, this is the Iwasawa algebra. This is defined to be the inverse limit over these group rings Zp, G mod, let me write Hn, where G mod Hn is isomorphic to Gn. Hn are open normal subgroups in G. So these are actual group rings, and then you check the inverse limit with respect to the natural maps. And then you get a completed group ring, which is now a very nice object. Because this is complete, so it gives you much more handle to grasp it. So for instance, in the simplest case, when G is gamma, then lambda gamma is just a power series ring in one variable, which is as good a regular commutative regular ring that you can ask for. It's local, regular, and so on. But the same definition works even if this is non-commutative, except you don't know much about the completed group algebra. And that was one of the things that we first did when we started on this non-commutative Iwasawa theory. So for G non-commutative, G arbitrary, let's say pro P, not necessarily commutative. And in all these cases, G is going to be a p-adic analytic group. In this case, lambda G is the closest you can get to a non-commutative analog of regular local rings. They are what are called Auslander regular rings. So lambda G is local, Noetherian domain, non-commutative of course, Noetherian domain, Noetherian domain in the sense of not having zero divisors. Domain, and it's going to be Auslander regular, which I will not say much about except to say that in the non-commutative world, this mimics what a regular local ring does in the commutative world. So in particular, when you have these Auslander regular rings, see, one of the great advantages when you are working in commutative setting or in the commutative world is you have dimension theory. So that helps you do geometry, that helps you do homological algebra and so on. But if you stare long enough at homological algebra, you realize that you don't really need commutativity. Homological algebra is agnostic towards commutative or non-commutative. So therefore, you can carry over the homological machinery to this context. And what is the characterization of regular local rings? Projective dimension is finite. Every module, every finitely generated module over that regular local ring has finite projective dimension. Now the same thing is true here. So you can do homological algebra here, and you get a corresponding dimension theory over these non-commutative rings. And for left, when I say modules over these non-commutative rings, I'll always mean left modules. So you have a dimension theory. So for instance, what's the dimension of lambda g? So Krull dimension of lambda g, I'm just calling it Krull dimension because it's the analog, but it goes under various dimensions, it goes under the name of Auslander dimension, etc., etc. But let me just, for simplicity, let me call it K. K dimension of lambda of G of this ring is, lambda is ZP, the coefficient ring is ZP, which carries one dimension, 1, plus this is a p-adic analytic Lie group. Most often that I'll be interested in, G will be a p-adic analytic group. So as a p-adic analytic manifold, it has a dimension, so you just add that dimension, plus D, where D is dimension of G considered as a manifold. Okay, and now in this world, it's nice to work with compact modules. I have those discrete modules there, and there's an easy way to make them compact. You just take the Pontryagin duals, and those are what I'll be considering. So I'll reserve the letter X for X of EP infinity over whichever ring that I'm considering, sorry, field I'm considering. L will typically be F cyclotomic or one of those F infinities. Okay, that's still there. And X EP infinity over L, this is by definition the Pontryagin dual of the Selmer group over L QP mod ZP. So then this is a compact. So all these Iwasawa algebras, they are topological algebras. So they come with a topology, and when you take the duals, these are compact modules over the Iwasawa algebras. Galois group of L over F. Okay? And like I said, when I say modules in the non-commutative context, I'll always fix a left module. Yeah? Sorry, which one? No, this is the Selmer group defined over that. I'm taking its Pontryagin dual, homomorphisms into QP mod Z. I'm calling that X of EP infinity over L. This is going to be a module over the Iwasawa algebra corresponding to ZP coefficients, Galois group of L over F. Sorry? Oh. All right, okay, so let me simplify this. I don't want to keep writing, so Selmer group will be written as SP infinity E over whichever field. And similarly, I'll reserve the letter Y for the dual of the fine Selmer group, Y of EP infinity over L. This is going to be the Pontryagin dual of R of EP infinity over L, QP mod ZP, and again, this is a compact module over this. Okay, so I like to think about this, when you're thinking about it in motive, because like I said, you can define all this in the broader context of Iwasawa ordinary representations, so representations coming from modular forms and so on. So in that setting, so when I'm thinking about that, then I don't think of the elliptic curve as much as I think about the motive coming from the elliptic curve, which is the Tate module, right? And that motive is already two-dimensional. The representation associated to it is two-dimensional. What's the simplest motive? The Tate motive. And the analog of all these have been studied in the Tate motive case as well. That is the classical Iwasawa theory. It goes back to Iwasawa's work on studying class groups. And also the Galois group over, so you take a big extension, start with a ground field F. Let's say typically you take the cyclotomic extension, so to fix P, so this is ZP. And then you take the pro-Hilbert class field of this. So let me call this X infinity. So this is the maximal pro-P extension, unramified everywhere. And take this Galois group. So Galois group of X infinity over F cyclotomic. Now this becomes a natural module over this Iwasawa algebra. lambda gamma, and this was what Iwasawa and many others studied. Abelian, sorry, pro-P extension, abelian, unramified everywhere. That's when only if it is abelian, then you get an action of ZP. This is abelian, so that induces an action on this Galois group, and this was the object that was classically studied. And these, in some sense, are extensions of that to the representations or to the motives coming from other Galois representations. Okay, so now what is so great about all this? This was what Serre and Iwasawa first discovered. Once you study them as modules over the Iwasawa algebra, then I'll keep this exact sequence because I'll need to come back to that. Right, once you take these, then this is not difficult. This is a non-commutative or topological version of Nakayama's lemma. The usual Nakayama's lemma that we study in commutative algebra will tell us that these dual Selmer groups, which I'm calling x of EP infinity over, let me just put L, by which I mean L is either F cyclotomic or any of those F infinity extensions. So these are modules over the Iwasawa algebra. So the first thing, which is very easy to prove, is that they are finitely generated modules over the Iwasawa algebra. Galois of L over F. So you have finitely generated modules, but in fact more. When this is abelian, so for instance, example, when L is F cyclotomic or Galois group of L over F is isomorphic to two copies of ZP, which typically arises in the CM curve context. When you take an elliptic curve with CM and then take its splitting, trivializing extension, then these are abelian, regular local rings. And then think of the classical structure theorem that you have for modules over principal ideal domains. It gives you a very nice structure theorem. There's a free part, there's a torsion part, and the torsion part are really divided, come from the elementary devices. But there, principal ideal domain, every ideal is principal. Whereas here, this is a regular local ring, so you know that height 1 ideals are principal. And there is a structure theorem in this case. This was due to Serre and Iwasawa. So they said the structure theorem is as follows. So let M be a finitely generated module over lambda gamma, let's say. Typically, I'll just be dealing with lambda gamma, so this is ZP double brackets T. Then M is pseudo-isomorphic. I'll come to this pseudo-isomorphic because we'll have to use this notion even in the non-commutative setting. Pseudo-isomorphic, so this just means pseudo-isomorphic, and I'll explain what this is. 2, there are certain copies of the free module, lambda gamma to the rank. This is called the rank of the module. Direct sum, lambda gamma, I equals 1 to k, say, lambda gamma, mod fi to the power ni. I'll write what these fi's are. Direct sum, certain copies of lambda gamma, mod p to the power mj. So what are these fi's? So remember this lambda gamma is ZP double bracket t. So I can use Weierstrass preparation theorem. These fi's are what are called the distinguished polynomials. So these are just polynomials. You can think of them as being elements in ZPT. But these are actually generators of height 1 prime ideals. So each of these denominator is corresponding to a height 1 prime ideal. So in that sense, it looks very much like the structure theorem for modules over PIDs. And then you have the special prime ideal P. So you isolate that. So this immediately gives you 3 important invariants. So let me write down those invariants. So the rank of M, lambda gamma of M, which is R. I'll talk to you about pseudo-isomorphism. And then lambda invariant of M. This is the summation of the power ni times the degree of that polynomial. I equals 1 to k. And there are uniqueness statements as well here, just as in the PID case. And then the mu invariant of M, which is the sum of the powers of P that occur. what did I call it? K, Mj. So these are three important invariants that are associated to any finitely generated module, yeah? Oh, sorry, let me call this T. They are not both K, let me call this T. Thanks. Now what is this pseudo-isomorphism? In the simplest case, when it is Zp double brackets T, then pseudo-isomorphism for lambda gamma, pseudo-isomorphism just means that the kernel and co-kernel are finite. So there is a homomorphism from this to this with kernel and co-kernel finite. But for arbitrary Iwasawa algebras, when they are commutative, non-commutative, you still have a notion of pseudo-isomorphism. In order to do that, you need to define when a module is pseudo-isomorphic. And that's where the dimension theory kicks in. Remember I said that these are great because it affords a dimension theory. So therefore you can define pseudo-isomorphism, you can define torsion. So let me do that. So I'm always in this setting. I'm considering Iwasawa algebras over pro-finite, pro-p groups, but they need not be abelian and they need not be commutative, okay? And it coincides, the extension to the non-commutative case coincides with the notion of pseudo-isomorphism in the commutative case. So first, so what is torsion? A module M, so let me now get back to lambda G, where G is, as I said, pro-p, p-adic, analytic, and so on. So M is torsion, lambda G module, if, remember I said it comes with a dimension theory, so the dimension should be 1 less than the dimension of the ring, which is the case even in commutative algebra. You say something is torsion if it has Krull dimension 1 less than the dimension of the ring, right? Or equivalently, it's the same thing. You tensor it with the fractions. Remember, this is a domain. So there is the skew fraction field. When you tensor it with the skew fraction field, you get 0. So they are all coincide. All these definitions coincide. And then M is pseudo-isomorphic, pseudo-null, okay. Pseudo-null if dimension of M, so M is of codimension 2. So in comparison with the ring, it's much smaller. It's at least 2 steps smaller than the dimension of the ring. So for instance, when you come back to this case, this is dimension 2. So pseudo-null means come down 2 lower, that is 0, so it is finite. Okay? So in general, this is said pseudo-isomorphism if there's a map and the kernel and co-kernel are both pseudo-null modules. Okay, so now let's get back to Iwasawa's classical mu equals 0 conjecture. So yes, that's this module here. Okay? So this is a module. So it has that structure theorem. So the first big result that Iwasawa proved was that it was torsion. And so once it's torsion, there is no free part, and you only have the lambda invariant and the mu invariant. And they also proved that this, remember it's pseudo-isomorphic, so in principle there's a map like this with finite kernel. And Iwasawa also proved that that one has no finite submodules. So it literally injects into something looking like this and something looking like this, right? And the other invariant that comes from the structure theorem, it's what's called the characteristic ideal. Of M, CH of M. This is all in the commutative case still. So CH of M, this is the ideal generated by the product of the Fi's times the product of the Pi's. Fi Ni, Pi Mj's. Just collect all these height 1 prime ideals, take their product, take the ideal that it generates. That's called the characteristic ideal. So now I have somewhat given you the picture of the objects that we are studying on the algebraic side. Okay? And what was the main conjecture in Iwasawa theory, the classical Iwasawa theory? So you have an object here, you have a characteristic ideal, which is an element in the Iwasawa algebra, in the simplest case when you take lambda of gamma. And the main conjecture tells you that there's a p-adic Riemann zeta function, which again you think of a measure as a measure and therefore as an object in the Iwasawa algebra. Now this p-adic L function interpolates the values of the usual Riemann zeta function, and the main conjecture tells you that for that Galois group, the characteristic ideal that you get from algebra is also generated by the p-adic L function. So that's the link. And something similar happens for Selmer groups. The main conjecture predicts that when you're in the commutative case. In the non-commutative setting, it's much more complicated. I will not talk about that. But in the non-commutative setting, you can now imagine you want to get your hands on the right algebraic object, but then you don't have a structure theorem. You only have a concept of pseudo-isomorphism. You have a weak structure theorem. There is a pseudo-isomorphism, there's a free part, plus a torsion part. And the torsion part, you no longer know that the height 1 prime ideals, even defining a prime ideal in the non-commutative situation is dicey. So all you can say is here, instead of these, you have ideals, special kinds of ideals. And you no longer know they are principal. So you don't get your hands on a single element. So therefore the whole picture becomes complicated. I'm not going to get into that. But suffice it to say that classical Iwasawa's mu equals 0 conjecture predicts that if I take F a number field, P a prime, then mu of, let me call this script x or something, okay? Then it says that mu of x is 0. That is the classical Iwasawa theory conjecture. And you know that it's true for Q, abelian extensions of Q. That was one of the big theorems Ferrero-Washington proved and so on. And you can retranslate this. In fact, in Galois cohomological terms, what you can do is retranslate this as a combination of these two. H2, Fs over F cyclotomic, Qp mod Zp is 0. This is called the Weak-Leopold conjecture. This is this one, this Galois group, the classical object that one is studying. Plus H2, Fs over F cyclotomic, Z mod P is 0. So these two combined together is equivalent to mu equals 0. Okay? And so now we want to see what can be done for the Selmer groups, because we made this grand analogy between classical Iwasawa theory, study of Selmer groups and class groups and so on. And so here, I'm going to erase this. You no longer expect when I take the Selmer group, when I take these dual Selmer groups over the cyclotomic extension, you no longer expect the mu invariant to be 0. In fact, Mazur already produced examples where the module was torsion. This is a deep conjecture of Mazur, going back to the 80s or 70s, I think, who conjectured that in the ordinary case, let me write that, x of EP infinity over F cyclotomic is, we know that it's finitely generated, but he conjectured that it is torsion as lambda gamma module. And we have generalized this. We understand when a statement like this can be expected to be true when you go to non-commutative extensions. I'm always going to be working with extensions that contain the cyclotomic. And the conjecture is that in the ordinary case, this dual Selmer group over here is again torsion as a module over the Iwasawa algebra. And note that torsion makes sense now because I have dimension theory. So the dimension is 1 less than the dimension of the ring. That's the conjecture. So we no longer have this analog of Iwasawa's mu equals 0 conjecture for the Selmer group. Nevertheless, we do conjecture, this was a conjecture. Oh yes, of course, this was proved, I should mention this, this was one of the big results in Iwasawa theory, proved by Kato, when F over Q is abelian. And in fact, it comes up in the proof of the main conjecture. I forgot to mention that, but why is the fine Selmer interesting? Because the fine Selmer shows up in the main conjecture. Okay. So now this was a conjecture that Coates and I formulated sometime at the turn of this century, we conjecture that irrespective of, so Mazur made this conjecture for the ordinary case, he assumed P was ordinary. But irrespective of the nature of reduction of the elliptic curve at P, we conjecture that the fine Selmer group, the dual of the fine Selmer group, y of EP infinity over L, where L can be now F cyclotomic or any of those extensions F infinity. This is torsion as a lambda Galois group of L over F module. Yeah. Yeah. So the local conditions.
Can you give us a clue like between S and R of X and Y, there's inclusion or exclusion?
Exactly. So the fine Selmer group in the discrete case, it's a subgroup of the Selmer group. And what comes into the co-kernel are injections into the local H1s where you only have P. Y is a quotient of X. So if you know it for the Selmer group, you know it for the fine Selmer. But the point is you don't expect it to be always true for the Selmer. Right? Like I said, Mazur already came up with examples where the mu invariant for the Selmer group in ordinary elliptic curves was not 0. But for the fine Selmer, which is a quotient, we always expect it to be 0. And one further analogy to show that this is the right analogy with Iwasawa's classical mu equals 0 conjecture. So we have mu of, so let me call this, so conjecture, we call it conjecture A. There's another conjecture which we call conjecture B, so this is conjecture A. So to push home the point that this is the right analog of Iwasawa's mu equals 0 conjecture, it's easy to see that conjecture A is true if and only if H2 Fs over F cyclotomic EP infinity is 0. This is weak Leopold for elliptic curves plus H2 Fs over F cyclotomic EP is 0. So you see this is the exact analog for the motive coming from elliptic curve. Initially you had the trivial motive and this is the exact statement for, yeah. Can you speak louder? Oh, sorry, y equals torsion as Galois. This is, okay, plus mu equals 0, sorry, yeah. So it is torsion and mu equals 0. Now torsion part follows from Mazur's conjecture because Mazur conjectures that the dual Selmer group is torsion. And the dual fine Selmer group is a quotient of the dual Selmer group, so it has to be torsion. But we conjecture that the mu invariant is also equal to 0. Okay? And it has note the striking analogy between the classical Iwasawa's conjecture and this one. All right, so now what can we prove in this case? Okay, yeah, the next conjecture that we made was called conjecture B. So, yeah. So let me, yeah, I can remove this Iwasawa's classical conjecture. So I'm in this situation, so I have Fs, I have this big extension F infinity, I have F cyclotomic, I have F. This is gamma, this was G, I'm going to call this H. And I have the fine Selmer group over this big extension, which is a module over the corresponding Iwasawa algebra lambda of G, which we conjecture is torsion, which is true if conjecture A holds, then you know it is torsion. But we conjecture that it is pseudo-null. So conjecture B, so I call the dual fine Selmer group y of E over F infinity, EP infinity over F infinity, is finitely generated as a lambda H module this time. So note that H is a subgroup of G. So the Iwasawa algebra of H is a subalgebra of the Iwasawa algebra of G. And we are saying when you restrict scalars and view it as a module over lambda of H, it is already finitely generated as a lambda H module, which forces it to be torsion. So it is torsion. And then in this non-commutative context, the P part of the structure theorem still holds. So you can define a mu invariant. and we conjecture that it is pseudo-null. So it is finitely generated as a lambda H module and torsion as a lambda H module. So this together, this is equivalent to saying that this is pseudo-null y of E infinity is finitely generated and pseudo-null, that is, its dimension is at least 2 less than the dimension of the Iwasawa algebra. Pseudo-null as a lambda G module. Okay, so this was done around 2000. We could come up with lots of examples where conjecture A holds, but conjecture B, the examples were kind of sparse. So let me state the results that I have proved. These are recent results. So I can now state the theorem. Theorem 1, this is recent work with Debanjana. She's a student at University of Toronto, but who's being co-supervised with me. And this says the following: let F be a number field, E over F an elliptic curve of rank 0, good ordinary at P, at all the primes above P, and we need this strong assumption. Assume that the Tate-Shafarevich group of E SHA is finite. This is a tricky assumption, not just for this elliptic curve, but for all elliptic curves over F. So assume that SHA is finite for all elliptic curves over this number field. Then for density 1 primes, we can show this very strong condition that the Selmer group over the cyclotomic extension is actually 0. So a very strong form of conjecture A holds. So the fine Selmer is 0, the Selmer is also 0. Okay, so that's evidence for conjecture 1, and this is the first time that there has been a sort of, unified class for which you can, unified hypothesis so that you get a class. Otherwise, the earlier examples were for small primes, and it was going through the Selmer group. You go to the Selmer group, wherever the main conjecture is known, you compute the p-adic L function, the mu invariant is 0, so therefore the mu invariant has to be 0 for the fine Selmer group. That was the way the examples went, but this is giving a unified, you're viewing this through a unified lens. Okay, for conjecture B, so there's this classical, what's called generalized Greenberg conjecture, So which is the following, I'll state it only in this context. Let's take F, I want to state it the way Greenberg stated it, so I'll have to look at my notes. Yeah, so he does it for arbitrary number fields. F is a number field, P is prime, and I think he even allows P to be even, but let me assume it's odd, P odd prime. Now F tilde is the composite of all ZP extensions of F. So you take, and of course Leopold, if you believe the strong Leopold conjecture, it's going to tell you how many ZP extensions there are. Okay, so take the composite of all ZP extensions, and then you define, exactly as we did for the cyclotomic extension, you define the pro-P Hilbert class field of L tilde. So you have your F, you have F cyclotomic is inside because it's one of the ZP extensions, you have F tilde, and then you have L tilde. This is the maximal pro-P abelian everywhere unramified extension. Yeah. Of F tilde, sorry. Okay, so earlier in Iwasawa's case, we took the pro-P Hilbert class field of F cyclotomic, and the mu equals 0 conjecture was a statement on that Galois group. So here you are going to the composite of all ZP extensions, and then you are looking at that. And Greenberg's conjecture, so now you are in the commutative case. So you have the usual dimension theory. So Greenberg's generalized conjecture says that, let me call this X tilde, which is the Galois group of L tilde over F tilde, which is now a module over this Iwasawa algebra, which is as many ZP extensions there are. So if there are R ZP extensions, this is ZP power series ring in R variables. So this is pseudo-null. As a lambda Galois group of F tilde over F module. So since I don't have much time, I'll just state, just as in the conjecture A, we showed that it was related to Iwasawa's mu equals 0 conjecture, we can show that conjecture B is the analog of Greenberg's generalized Greenberg conjecture. And this conjecture has been numerically verified for, I don't know, 12 million primes, the first 12 million primes or something. All right, so here is what we can prove for related to conjecture B, theorem 2. This is again joined with Debargha, and we show okay, let me get the hypothesis right. We are just writing this down. So we are assuming F over Q, number field, mu P, the pth roots of unity contained in F. P does not divide the class number of F. So this is the analog of regular primes. So for instance, if F equals mu P, then P is a regular prime. Yeah? Which one? Which is Greenberg's conjecture? Greenberg 0. Greenberg conjectures that lambda equals. Yeah. So there's a strong, that's called a strong Greenberg conjecture. So this is called a generalized Greenberg conjecture. So this doesn't divide, so this is a regular prime. So for instance, if F equals mu P, this is the notion of regular primes. So then in this case, let's take, yeah, and then I need to assume that P is totally ramified in F. And then suppose take G to be a pro P extension. Now F infinity is one such extension. F infinity of F is a pro P extension. And E over F an elliptic curve. Then conjecture B is true. Okay, this is the second theorem. And to say, I'm not going to write it out. So a version of this theorem, when I take a quadratic imaginary number field, take an elliptic curve defined over that quadratic imaginary number field and containing the p torsion points being, okay, F should contain the quadratic imaginary number field and also the p torsion points, so that the trivializing extension becomes ZP cross ZP. Okay, that's a CM case. And there, we show that conjecture B in that context is equivalent to Greenberg's conjecture. For that, because you're in a totally imaginary case, so you have ZP cross ZP, and from the elliptic curve, CM elliptic curve, you get another ZP cross ZP extension, they are the same, and those conjecture B then matches up with Greenberg's generalized conjecture. So both these conjectures were formulated in, like I said, sometime around 2000, and evidence was very sparse, yeah. Sorry? Yeah, we can prove it in this generality. It's any pro P extension, but you need these hypotheses for regular primes. For the analog of regular primes, we can prove it. No. for this, surprisingly not. No. Okay, and I mean, just being regular, this shows that being a regular prime somehow comes with a whole lot of goodies. Okay, so now, P, yes, elliptic curve over, yeah, ordinary at P. Well, this we are still trying to understand if we can relax the ordinarity hypothesis, but I know that it works for ordinary, and we are confident we can push it through even the supersingular. Correct, because our initial conjectures, conjecture A and B, has nothing to do with the type of reduction at P. Okay, so I want to close with these two very intriguing examples. So if I may, I'll just take 2 more minutes. So when we first stated these conjectures, for conjecture A, there was a lot of evidence. Conjecture B, we wanted to provide concrete numerical evidence, and we were stuck, you know. So here is the example, the numerical examples we considered when we formulated this conjecture. So E is over Q, and E is this elliptic curve, y squared plus xy equals x cubed minus x minus 1. This is B1 in Cremona's tables, conductor 294, no CM. So it's really a non-commutative context. And then we take the prime P equals 7. We take the base field F to be Q mu 7. And then F infinity is a trivializing extension, Q mu 7 infinity. And F cyclotomic is the Z7 extension. So in this setting, what we can show by usual classical cyclotomic theory, in fact, you know that the Selmer group vanishes over the ground field, it vanishes even over the cyclotomic. By the way, there is a little bit of perfectoid spaces tucked in here, no, though not in that language. To go from the cyclotomic extension to F, to compare that, you're really studying local norms. You're studying the norm groups, and which you do in the language of Fontaine and Debargha field of norms. So this is 0. And so therefore the fine Selmer group, of course, it's strong, it's very strong. You know that the fine Selmer group itself is vanishing. So y of E over F cyclotomic is 0. But what about the fine Selmer group over the trivializing extension? Y of E over F infinity. So what is S? S is the prime suburb 2, 3, 7. This is our S. So we can even show in this case that this is 0. But at that point we couldn't. We could only show that this is, as a lambda G module, it has rank either 2 or 0. And we couldn't eliminate the case that it 2. Because you want it to be torsion, right? So we couldn't eliminate the case of being rank 2 not over lambda G but over lambda H. Remember, conjecture B says that it's finitely generated over this and it is torsion over this. No, Q mu 7 infinity. No, F cyclotomic, oh sorry, QE7 infinity. Sorry, yeah, the trivializing extension. So at that point, we couldn't show that this was, conjecture B was true. But now our methods show that this is true. And the other example, this is the most interesting one according to me. And for me, it proves the value of trying to understand Galois extensions of Q, which is after all why we do algebraic number theory. So conjecture B, so this is the second example. Take E to be y squared plus xy equals x cubed minus 3x minus 3. This is defined over Q. This is the curve A1 in Cremona's tables, conductor 150, again non-CM, and the set S are those dividing the conductor, so S is V over 2, 3, 5, and I pick P equals 5, and I take the same notation, so E5 infinity and mu phi infinity, the cyclotomic Z phi extension and E5 infinity. So at that point, we could only show that conjecture B is true for the fine Selmer group Y over the trivializing extension if E has a point, if the elliptic curve has a point of infinite order over the trivializing extension. So this is all we could show at that time. And I remember John Coates being very confident saying, oh, we can just talk to all those computational guys and I'm sure they'll set their machines running and within a few days we should be able to decide whether we can find a point and so on. And they tried finding points over mu phi, E phi squared, E phi cubed, and there was a special year in Berkeley, and by the end of the special year, nobody could tell us whether there was a point or no point. And in the intervening years, in the last 20 years, despite significant advances in computing techniques and computing algorithms, last year I asked the current experts, and they said, oh, I kept my computer running for 2 months and it still hasn't come up with a point. But today, our theoretical methods show that this is true. And in fact, the way we proved it, if this is true, then it has to have a point of infinite order. Also, it's an if and only if. Somehow it had consequences. If it had no point of infinite order, then that would somehow be not an example for conjecture B. So this current methods are telling us that conjecture B is true, and also because it is true, you can deduce that it has to have a point of infinite order over F infinity, purely theoretically. Sorry? F infinity is F of E5 infinity, the trivializing extension. Sorry, this is Q, you can take Q E5 infinity. This is defined over, yeah, you can take F. F is Q mu phi, for instance. We show that it's actually equal to 0, that the whole fine Selmer group is 0. And in this example, we show that it has rank 0, so it is torsion. We don't know that it is 0, we show that it is torsion, but we show that it has a point of infinite order over 0. So 20 years of computing power didn't work. They said they could go only up to E phi cubed, and they couldn't find a point there. So I'll stop here. I wanted to say more about the ordinary supersingular case and congruences. Let me just say one sentence, and that is in these 3 pictures, you see you have Greenberg-Wurzel, which tells you about congruence between L values, critical L values. The analog of that here would be congruence between p-adic L values. When 2 representations, take 2 elliptic curves, if the residual representations are isomorphic, then Greenberg-Wurzel tells you that the complex L values are congruent mod P. P-adic L values should be congruent mod P. We can show that on the algebraic side, the Euler characteristic, which is the analog of those, they satisfy a congruence mod P. If one is a unit, the other is a unit. We can do it even in the supersingular case by similar methods. And our method of analyzing the supersingular case is somehow unified. It gives results simultaneously for the whole Selmer group and the signed Selmer groups in one stroke. So I'll stop here and thank you very much.